Welcome to Chapter 5, beginning of Unit 3. In this lesson, we're going to be looking at work and the work in the physics sense, as well as the equations that are appropriate when you're trying to solve through for work in physics. And then we are going to continue with looking at kinetic energy, its equation, and the relationship between its variables. So to start us off, we have three definitions of when work is done. Please copy these down, guys. First one is a force causes a displacement of an object. A force causes a displacement of an object. In other words, you apply a force to an object and it's going to move. So if you apply a force to an object and that object moves in relationship to it, then work is being done. Well, kind of. We're going to have to be a little bit more specific on this. So this is extremely generic for you guys to look at a definition. Your second definition says work is done when it equals magnitude of the force times magnitude of the displacement. So equals magnitude of the force times magnitude of the displacement. So once again, we see that force and displacement are going to be your key variables in determining work in the physics sense. But this still isn't good enough. It's this third definition that we really want you guys to hone in on. Listen to this. It says an object is moved with the action of a force parallel to the distance traveled. Okay, an object is moved with the action of a force parallel to the distance traveled. Jot that down and then we'll discuss it. So those are your key words on this. In order to say that work is being done in the physics sense, you have to have a force that moves an object parallel to its direction. So for instance, look at this server here. Let's see what this cartoon means. This server says, wow, this is great pay for doing no work. That must be a physics major, right? Okay, so apply why they are saying that this is easy work, great pay for doing no work. Well, they're doing no work because your force is pushed up. You're pushing up on the tray, agreed? But you're traveling this way. So that would make them perpendicular to each other. Since they are perpendicular to each other, no work is being done. So you apply a force, the object has to move parallel to that direction. You'll see later that it could be either a positive or a negative. So I push towards the right, the object moves towards the left. That's cool. That's still going to be work. So the general equation that we would look at is work equals force times distance. But to be more appropriate and to say that and verify that work and distance are going to be parallel to each other, we want to use W equals FD cosine theta. Really, and I don't think Mr. Dillick's going to run with this too much, but that's fine. Just like, with AP for him and IB for me, we have our students look at W net equals F net times D times cosine theta. Because really you're looking at the net work done in this whole entire system, the grand total of forces. Did it move? Did the system move? Did the object move based on that? So looking at this, W stands for work. Your force is going to be your F, and force is measured in newtons. And your D is going to be your displacement. I know it looks kind of goofy, right? Because we know displacement as X, but your displacement will be measured in meters. So technically work is going to be a Newton meter. We call a Newton meter a joule. Okay, so a capital J is what you're going to simply use for your units then for this. So looking at this scenario then, we can see that work is being done. And if we click on this little picture here, you'll be able to see that in this scenario, as the cart is being pulled up the hill here, no matter what the degrees are at 30, 45, and 60 respectively, that work is being done in the system. Check out the numbers that are changing as they are moving through this system here. Force is 9.8, it's moving a distance of, therefore there is work. So work can be applied to things that are on angles as well. Okay, so this one right here. If your F and D are working parallel to each other, that'd be cosine of 0 degrees. Agreed? Make sure you're in degrees. So make sure your mode is in degrees when you're working with this unit, i.e. chapter 5. So if your cosine is 0, then that's going to be 1. Therefore, work is done. You would be able to calculate work in that scenario. If your cosine was 90 degrees, though, that would mean that your distance or displacement of force were perpendicular to each other, so that's going to be 0. So therefore, work is not done. You're not going to be able to say what the work is in the physics sense. For cosine 180, that's like a -1. That would mean that your force and distance are working opposite each other, but work is being done in this scenario. So we can still calculate a value, some quantity. So for this, if you are at an angle, obviously you need to remember to draw your triangles, break them into vectors, etc., etc. That's really all I want to say with that. Just remember that you guys want to do that. This idea right here, obviously it's talking about the x component of a bow tie triangle. So in other words, and then I'm just going to call this f. So this is like f of x and f of y, where this is adjacent and x is adjacent. Therefore, you would use the cosine function. Okay, another equation. Here we come more specifically. W net equals f net times d times cosine theta, in which work is seen as a scalar quantity, which is magnitude only. Okay, so talk about acceleration. If an object is moving at a constant velocity, what can you tell me about the acceleration? If you're moving at a constant velocity, your acceleration is 0 meters per second squared. Agreed? So what does this mean about the force that's acting on it? So support it with an equation. We got F equals ma, right? Well, if your acceleration is 0, F and A are directly related to each other. So if F and A are directly related to each other, that means that you have 0 newtons working on this system, i.e. forces are balanced. Now, if they're balanced, that does not mean that it's at rest, right? It could still be moving at a constant velocity, in which this scenario it is moving at a constant velocity. So please make sure that you understand that Newton's second law of motion is going to be applied to the work big time. So positive work, negative work, and I really don't want to write anything down on this slide, but take a look at this. So you're pulling this way on this car, and it travels that way. So that would be negative, right? So that would be like a cosine of 180 degrees inevitably. But if they're traveling with each other, then that would be like a cosine of 0 degrees. Now, clearly you guys understand that these are not 180 and 0 because they are being pulled at an angle currently in these situations. I'm just trying to get you to think that it is possible that you could move something one way, push on something one way, and it can go back the other way. So please take a second and look at these ideas here and decide which ones do generate work. By looking at which ones generate work, you'll be able to say that you totally get this. So a teacher applies a force to a wall and becomes exhausted because the wall doesn't move. Well, there's no work being done, right? So you just click on C answer, and then it'll pop up and tell you, no, this is not an example of work. The wall is not displaced, so therefore there is no work that is being done. Please make sure you look through those. We definitely did choose some of them for multiple choice questions, just saying. Okay, so your example problem here. How much work is done on a vacuum cleaner pulled at, so we have a distance of 3.0 meters, at a force of 50.0 newtons, and an angle of 30.0 degrees. So how much work? Do you remember what the units were for work? They were joules, okay? So with that in mind, you want to make sure you're in degrees again. And then your general equation is FD cosine theta We don't need to rearrange anything, nor do we need to change any variables. So please get your calculators out. Please don't just let us do the work for you. Get your calculators out. Cosine 30 times 3 times 50. Cosine 30 times 3 times 50. Calculator answer should be 129.9. Looking at your number of sig figs here, you only want 2 sig figs, so therefore 130 joules is your final answer. For my kiddos, 1.3 times 10 to the second joules. Okay, look at those scientifically notated answers. And then finally, to wrap it up, look at this physicsclassroom.com here and see if you understand what work is. My students will be looking at this further as a demonstration of are you getting this or not on the next day. So then moving right along, we have kinetic energy, which is defined as the energy of motion. And it's going to depend on the mass of the object and the velocity of the object. Okay, these are going to be two variables that you're going to have to keep straight, mass and velocity. So the equation that we are going to use here is Ke equals 1/2 mv squared, whereas m is your mass, measured in kilograms, and v is your velocity, measured in meters per second. So therefore, Ke is your kinetic energy, which looks like it's going to be measured in kilograms times meters squared seconds squared, right? Because it's being squared up here, so meters squared seconds squared. That's the same exact thing as a joule, guys. So your kinetic energy is going to be measured in joules. Also, kinetic energy is going to be a scalar quantity for you to look at. So let's look at this example here. Bowling ball and a volleyball. They're being moved at the same velocity. So in Ke equals 1/2 mv squared, your velocity is what is constant. So what is the relationship between mass and kinetic energy? Well, it's a direct relationship. So therefore, as the mass increases, more kinetic energy occurs in the system. So the bowling ball would have a greater kinetic energy because it is more massive. Okay, bowling ball because it is more massive. Sample problem B here. You go into the problem knowing that you have a mass of 7.00 kilograms and your first velocity is 3.00 meters per second. You want to figure out how fast a second object at 2.45 grams needs to move in order to have the same kinetic energy as the bowling ball. So ultimately you want to figure out the V2 in meters per second. So you first want to figure out what your kinetic energy, let me stay standard here, the kinetic energy of the first object is, because then you'll know what the kinetic energy of the second object is. So the first object is going to be 31.5. So Ke1 equals 31.5 joules. Therefore, Ke2 equals 31.5 joules. So Ke2 equals 1/2 m2 v2 squared. Check this out though, guys. You need to change units on that. Make sure that you change your units on that. Okay, and then we need to rearrange it, and when we rearrange this guy, we're going to get the square root of 2 Ke2 all over m is going to give us our V2. Plugging into this is going to give us 2 times 31.5 divided by 2.45 times 10 to the negative third. Putting that in your calculator gives you 160.36, which gives you 1.60 times 10 to the second meters per second for your second velocity. So for homework tonight, you need to do your practice A and your practice B problems, in which the answers are on my teacher page. All right, good job. Tomorrow will be C and D.